Good day, everybody. We are the 7th presenter for class group number 2 here to introduce you to route surveying, presented by Cesar, De Guzman, Hitalig, and Teves.
Now, what is route surveying? Route surveying is the plan, design, and laying out of routes such as highways, railways, canals, pipelines, and other linear projects. A survey is made to physically establish a location in the field. It includes the location of all man-made features in relation to the established roadway centerline in such a manner that these features can be accurately indicated in the plans. The term route survey refers to surveys necessary for the location and construction of lines of transportation or communication that continues across the country for some distance, such as highways, railways, open conduit systems, pipelines, and power telecom lines. Generally, the preliminary survey for this work takes the form of a topographic survey. Now, what is the purpose of route survey? Now, the purpose of route survey is to provide critical information regarding the existing roads and bridges condition, terrain, and other route constraints. A route survey is usually required for the planning of right-of-way, the acquisition of fee or easement of property, and for eventual construction layout work. The location of the facilities within the right-of-way are often held in respect to the center line or a right-of-way line. A route survey is made on the ground to provide for the location of right-of-way lines, a center line or reference lines in relation to property lines and terrain features. Route surveys shall include but are not limited to the proper location, monumentation, description, or platting of the following routes. Examples are roadways or highways and railroads, the transmission lines for communication, fuel, chemical, water, and electrical needs, canals, waterways, drainage, ditches, and sewers, and view easements, airspace easements, ingress and egress easements such as approach routes. But there are two route survey main aims: determining the best route between two terminal points, and fixing the alignment and grades of selected route. Now, at A, planning with respect to road construction takes into account of present and future uses of the transportation system to assure maximum service of the minimum of financial and environmental cost. The main objective of this initial phase of road development is to establish specific goals and prescriptions for road network development along with the more general location needs. These goals must result from a coordinated effort between the road engineer and the land manager, forester, geologist, soil scientist, hydrologist, biologist, and others who would have knowledge or recommendations regarding alternatives or solutions to specific problems. The pattern of the road network will govern the total area disturbed by road construction. Now at B, road alignment is the positioning of the center line of the highway or road. It is also called highway alignment. Simply, it is the direction through which the road will pass.
Moving on to the important structures of route survey. Route surveys include locating proposed new transportation systems or surveying existing routes for modifications or improvement. Route surveys shall include but are not limited to the proper location, monumentation, description, or platting of the following routes. First, we have roadways, highways, rapid transit, and railroads. So a frequent task of surveyors is to stake out the position of a transportation route. This is usually for the construction of a new railway line and highways between two places wherein proper surveying is required. The goal of surveyors is to locate the most direct and efficient route possible. Members of the route survey team can give route and grading recommendations to assist engineers in preparing plans. Next, we have transmission lines for communication, fuel, chemical, water, and electrical needs. We also have canals, waterways, pipelines, drainage ditches, and sewers. So a route survey is a data collection operation to gather information not only for proposed route of a roadway or railway, but also for power transmission lines, pipelines, canals, sewers, etc. Most of the basic surveying concepts and methods described in the previous chapters apply to route surveying. Horizontal distances, elevations, and angles must be measured, maps must be drawn, and profile and section views of the route must be prepared. Lastly, we have view easements, airspace easements, ingress and egress easements such as approach routes. So an airspace easement is a property right acquired from a landowner for the use of airspace above a specified height. They acquire easements to ensure that objects such as trees or buildings do not penetrate this airspace, creating a flight safety hazard. So these easements can be located and determined through route surveying. So here are some of the structures and routes that are being staked out during route surveying. Again, we have airspace easements, canals, transmission lines. We have railways, highways, and pipelines. Now let's discuss the features of route survey and design. So surveys are required for all types of route alignment, planning, design, and construction work. So route surveys range in complexity depending on the size and scope of the project. For complicated projects such as building a new highway or public road, they definitely require a lot of tasks and they undergo different processes. The surveyors must also work extensively with the contractors, governments, and landowners involved to prepare documentation outlining all of the steps necessary to safely construct a new roadway on a given piece of land. Small jobs involving simple road widening or minor improvements may be relatively simple and require a minimum amount of information necessary to prepare plans and specifications. So usual contracting requirement requires that the job must be done in the shortest possible time at the least possible cost, hence they don't usually use a lot of surveying instruments. Also, if conducted properly by an astute and experienced surveyor, they can definitely save a lot of time and expenses. Lastly, large complex projects such as a brand new multi-lane highway will involve extensive data collection to determine the best location, to prepare plans, specifications, and estimates for construction, and to prepare the legal documents and maps required. So, complex projects depend on so many variables, hence they require extensive data, sufficient funds, and enough time. The size of the property being surveyed is another contributing factor in the complexity of surveying projects, since the larger the property, the more time it will take to finish and the more information you need to acquire. So it is the function of the project surveyor to plan the surveys and collect the survey data needed to plan and lay out the final design. This will include, first, planning and establishing horizontal and vertical control. So horizontal and vertical control are established to provide a foundation or framework which other surveys can be adjusted. These control surveys are utilized for precise mapping in the construction of underground utility systems, highways, power lines, tunnels, and a variety of other high-precision projects. The district survey party chief decides if this control becomes the preliminary line. If done correctly, this layout method facilitates efficient use of the survey information by all project staff. Any adjustments to the location of the proposed improvement can be made without waste of survey work. Next, topographic surveys. So generally, the preliminary survey, a type of comprehensive survey, takes the form of a topographic survey. So the purpose of preliminary survey is to prepare an accurate map of the belt of the country along the selected route and estimate the cost of the project. Lastly, construction surveys for design location. Before construction surveys are done, a route survey is made to physically establish a location in the field. It includes the location of all man-made features in relation to the established roadway center line in such a manner that these features can be accurately indicated on the plans. So route surveys include both horizontal and/or vertical plane surveys. Horizontal and vertical plane surveys are developed to create a framework. These surveys are used for accurate mapping projects in the construction of various high-precision projects. So alignment is the shape or geometry of any transportation route. It is the position or the layout of the center line of the highway on the ground. Alignment surveys are widely provided for safety and protection purposes of different routes and highways. Highway alignment includes horizontal alignment and vertical alignment. The projection of highway alignment in the horizontal plane is termed as the horizontal alignment, and the projection of highway alignment in the vertical plane is called vertical alignment. Alignment must be selected in such a way that the overall cost during construction, operation, and maintenance is minimal. Next, route surveying operations. A comprehensive route survey consists of the following tasks in order. First, reconnaissance of terrain between terminals. The reconnaissance survey involves an examination of a wide area from one end of the proposed route to the other. It is the first step in selecting alternative routes. A reconnaissance survey is a rapid but thorough examination of an area, which is a strip of territory between the terminals of the project. It is carried out to determine the several possible routes which are worthy of detailed survey. For most projects, this would be done using existing small-scale maps and aerial photographs, although ground reconnaissance surveys may be used for the relocation of short sections of existing routes. In some cases, a complete topographic survey may be conducted so that an appropriate map can be prepared. Next, preliminary surveys over one or more locations along the general route. The preliminary survey may be conducted on the ground with surveying instruments or in the office using aerial photogrammetry. A preliminary survey is made of the best of several lines investigated during reconnaissance survey. The purpose of this survey is to prepare an accurate map of the belt of the country along the selected route and estimate the cost of the project. When there are two or more routes under consideration, preliminary survey is conducted along all the routes. Based on the survey and the data accumulated, final selection of the route is undertaken. Width of strip to be surveyed depends on the type of the project. So the basic product of the preliminary survey is the location of a baseline or connecting traverse. Lastly, location survey. Location survey is ground location of proposed line marked on the map. Main purpose of this survey is to make minor improvements to the line as may be desirable on the ground and also to fix the grades of the line. Line finally located on the ground is known as the field location.
Moving on to the general classification of terrain. The topography of the land traversed has an influence on the alignment of roads and streets. Topography does affect horizontal alignment, but it is more evident in the effect on vertical alignment. To characterize variations, engineers generally separate topography into three classifications according to terrain. First is the level terrain, the condition where highway sight distances as governed by both horizontal and vertical restrictions are referred to as level terrain. They are generally long or could be made to be so without construction difficulty or major express. Next, we have the rolling terrain. So as you can see based from the picture, it is the condition where the natural slopes consistently rise above and fall below the road or street grade. It is where occasional steep slopes offer some restriction to normal horizontal and vertical roadway alignment. So lastly, we have the mountainous terrain. So it is the condition where longitudinal and transverse changes in the elevation of the ground with respect to the road or street are abrupt, and it is where benching and side hill excavation are frequently required to obtain acceptable horizontal and vertical alignment. So the topography of the land traversed has an influence on the horizontal and vertical alignment of a highway. The terrain classifications pertain to the general character of a specific route corridor. So for design purposes, variations in topography are categorized by terrain. Next is the location survey. Location survey establishes all corners and property lines of the subject property to include finding or setting monuments. So the goal of a road location survey is to choose a route while keeping the following factors in mind. First is with a reasonable economy, it should fulfill the minimum curvature and grade requirements. Next, to create an easy-to-travel, free-flowing traffic artery with a large capacity that fulfills all safety regulations. Next, the roadside study should assess and analyze the route's influence on present industries, commercial, and residential values, as well as on future development. And lastly, historic, archaeological, and environmental sites will be disturbed as little as possible. Also, before beginning a field study for any highway location, a preliminary decision on the route's design speed, cross-section, and maximum gradient must be established. These decisions are based on the following criteria. First is to consider the estimated traffic volume, nature, and hourly dispersion, as well as the territory is traveled in order to gain knowledge about it. And lastly is to provide sufficient finances. So after the comparison of the different alternative design, the route is selected which has the cheapest overall cost, considering capital investment, maintenance expense, and saving to the road user. Next, we have the reconnaissance survey for highway location in rural area. So the objective is to identify several feasible routes, and the following methods can be employed by reconnaissance survey. So we have the conventional ground method and the aerial photography. So either or both of the mentioned methods are undertaken to identify factors such as terrain and soil conditions, serviceability, crossing of other transportation facilities, directness of route, and environmentally sensitive areas. Third, we have the preliminary location survey. So after the preferred location has been established, the preliminary location survey serves as the basis for fixing the actual highway location. So the economic evaluation of each possible route is considered along with environmental evaluation, as highway construction has a significant impact on surroundings. After having a preliminary location survey, there's also a need to conduct a final location survey. So final location is responsible in fixing the details of the projected highway. In this phase, detailed layout of the selected route is finalized, which includes horizontal and vertical alignments, positions of structures and drainage channels, trial and error process by the designer for engineering and aesthetic factors. The final location survey for roads is complete when all necessary information is available and ready for the designers to use. It ensured that all information required preparation of complete construction. Next, we also have the rural highway location survey and its design process. So first, we have the study of the area. So the possible area study for highways include engineering data, environmental data, social data, and economic data. So the following characteristics should be learned in the desk study of the area for location survey for roads. So here is an example of location survey for roads. So the following factors that was mentioned before and the criteria were strictly followed in order to come up with this location survey for specific road.
Next up are the factors to consider in design of highways. First is design speed. This refers to the highest speed at which vehicles can travel on the road safely when the weather is favorable and the density of traffic is low, while also ensuring that the safe speed is only determined by the road's geometric features. Next is level of service, which refers to the qualitative measure of functional conditions within traffic stream. This is commonly described as freedom to maneuver, travel time, speed, comfort, safety, convenience, and interruptions. This criterion differs for multi-lane highways and is defined in density. Next is traffic volume. traffic volume is the average density of traffic that will run on a road in an hour of every day. With the help of these volumes, service flow rate and other calculations will help to determine how the road should be constructed. Roadway context. The context of the road or highway is critical when developing a road construction project. This factor will determine fundamental design decisions like the cross-section termination, detailed design elements, and street fixtures to name a few. In order for a project to be successful, it is important for the highway design to consider its surroundings and perspective. A design that is context-sensitive will start with analyzing the contextual elements like the community and environment that surrounds the area. Once the designer clearly understands the surroundings of a potential highway and its users, the rest is much easier to design and plan. Sight distance. This refers to the length of the road ahead that can be seen by the user of the roadway. Most times, specific distances apply to cyclists and motor vehicles. Stopping sight distance, decision sight distance, and passing sight distances are usually taken into consideration. And lastly is safety. The safety that all transportation facilities provide is the primary consideration when it comes to geometric road design. While constructing roads, certain projects are specifically made to tackle existing safety hazards. It is important that all projects do eventually result in facilities that are extremely safe for its users. Conducting corridor safety audits and crash record analysis are a great way to discover any hidden safety hazards. It is important for designers to pick project design elements according to their expected characteristics, while operating and according to historic performance when it comes to safety. All highways are tested before they become functional. Moving on to the objectives of a preliminary survey. Its objectives are to, number 1, to survey the various alternative alignments proposed after the reconnaissance and to collect all the necessary physical information and details of topography, drainage, and soil. Number 2, to compare the different proposals in view of the requirements of the good alignment. And number 3, to estimate quantity of earthwork materials and other construction aspects and to work out the cost of the alternate proposals. There are two ways in conducting a preliminary survey. First is the conventional method. The survey party carries out surveys using the required field equipment, taking measurements, collecting topographical and other data, and carrying out soil surveys, which includes longitudinal and cross-sectional profiles of a level terrain, a rolling terrain, and a mountainous terrain, and also includes other studies such as drainage, hydrological survey, soil survey, traffic, and material survey. The other approach is the modern rapid approach. By aerial survey, taking the required aerial photographs for obtaining the necessary topographic and other maps including details of soil and geology. Preliminary surveys finalize the best alignment for all considerations by comparative analysis of alternative routes. Stopping sight distance is the distance traveled during two phases of stopping a vehicle: perception reaction time and the maneuver time. Perception reaction time is the time it takes for a road user to realize that a reaction is needed due to a road condition, decide what maneuver is appropriate, in this case stopping the vehicle, and start the maneuver, taking the foot off the accelerator and depressing the brake pedal. Maneuver time is the time it takes to complete the maneuver, decelerating and coming to a stop. The distance driven during perception reaction time and maneuver time is the sight distance needed. The design standards of the American Association of State Highway and Transportation Officials, or AASHTO, which is also used by DPWH, allows 1.5 seconds for perception time and 1 second for reaction time. The values of stopping sight distance used in design represent a near worst case scenario. For design, a conservative distance is needed to allow a vehicle traveling at design speed to stop before reaching a stationary object in its path. A generous amount of time is given for the perception reaction process, and a fairly low rate of deceleration is used. The design sight distance allows a below average driver to stop in time to avoid a collision in most cases. Driver perception reaction distance is calculated by D sub PRT is equals to 0.278 VT for the metric scale and d sub PRT is equals to 1.47 VT for the US customary scale or for the imperial scale, where d sub PRT is the driver perception reaction distance in meters or feet, v is the design speed in kilometers per hour or miles per hour, and t is the brake reaction time in seconds. Based on the results of many studies, 2.5 seconds has been chosen for a perception reaction time. This will accommodate approximately 90% of all drivers when confronted with simple to moderately complex highway situations. Greater reaction time should be allowed in situations that are more complex. Then we have braking distance, which is calculated by d sub mt is equals to 0.039 v squared all over a for the metric scale, and d sub mt is greater than or equal to 1.075 v squared all over a for the imperial scale, where d sub mt is the braking distance in feet or meters, v is the design speed in kilometers per hour or miles per hour, and a is the deceleration rate in meters per second squared or feet per second squared. A deceleration rate of 3.4 meters per second squared or 11.2 feet per second squared is used to determine stopping sight distance. Approximately 90% of all drivers decelerate at rates greater than that. These values are within most drivers' ability to stay within his or her lane and maintain steering control. Also, most wet pavement surfaces and most vehicle braking systems are capable of providing enough braking force to exceed this deceleration rate. Stopping sight distance is calculated by adding both reaction distance and braking distance. So we get the formula SSD is equals to d sub PRT plus d sub MT. For the metric scale, it is SSD is equals to 0.278 VT plus 0.039 V squared all over A. And for the imperial scale, it is SSD is equals to 1.47 VT plus 1.075 V squared all over A. Now to apply the formulas we just discussed with a sample problem. Patricia is contracted by a local government unit and is tasked to design a road that will be intersected by train tracks. If the design speed of said road is 35 km per hour and the perception time of the drivers is 2.5 seconds, what should be the stopping sight distance so that drivers will be aware of the obstacle ahead? First, we list down the given variables or the given values in the sample problem. So we have 35 km per hour for the design speed, 2.5 seconds for the perception reaction time, and the deceleration rate is always at a constant of 3.4 meters per second squared for the metric scale. Now to apply the formula. SSD is equals to d sub PRT plus d sub MT, which is translated to 0.278 VT plus 0.039 V squared all over A. And now we substitute the variables to their values. We get 0.278 times 35 kilometers per hour times 2.5 seconds plus 0.039 times the square of 35 kilometers per hour all over 3.4 meters per second squared. Now before we could input this line in our calculator, we must first convert 35 kilometers per hour into meters per second so that it will be easier for us to cancel SI units. We convert 35 kilometers per hour to meters per second by multiplying it to 1000 meters over 1 kilometer times 1 hour over 60 minutes times 1 minute over 60 seconds, which gives us 9.72 meters per second. And we input that to our equation line, so we get 0.278 times 9.72 meters per second times 2.5 seconds plus 0.09 times the square of 9.72 meters per second, all over 3.4 meters per second squared. Then we simplify the squared value, so we get 94.48 meters squared per second squared. And now we can simplify both d sub PRT and d sub MT, which is 6.76 meters plus 1.09 meters respectively, and we get an SSD of 7.85 meters. So in conclusion, the designed road needs 7.85 meters for stopping sight distance. Now here are the sources we used in making our report. So that concludes an introduction to route surveying presented by Cesar, T. Guzman, Ketalig, and Teves. Thank you and have a nice day.